Welcome back. In this section we will take a look at the Dalvik Opcodes. So this one is super interesting, and maybe we are able to understand our first program after this section, our first complete program after this section. Let's have a look. In the last section we have taken a look onto the following program. So we have done our typical analysis. We have identified parameters and return values, in this case 0 parameters, return value integer. We have also learned more about the P0 object and why we do have a local register even if we do not have a local variable over there. Alright, what we did not learn is more about the iGet instruction. And the question of course is, what is this iGet instruction and what does this iGet instruction? And how do I know that this one is taking the P0 value, storing it into V0? Well, I also got some help on this one. And the help I've got is the Dalvik Opcode instruction set. And this is a kind of list full of instructions and the corresponding description to what this instruction does. I couldn't find an official documentation, which is in my case super ridiculous that there isn't one out there, but I have found a super amazing site. And this site has most, maybe barely all instructions and the corresponding descriptions to them. And this site I really want to show you right now. So I switch to my Ubuntu VM, then I go into my browser of choice and I search for Dalvik Opcodes within Google. And this one over here, I do not want to pronounce this name because it will be definitely wrong, but really thanks to this one who has put this website online. So this is a nice list of all these instructions over here. And you definitely want to bookmark this site right now because you will use this a lot. I also looked them permanently up in this list over here. And let's have a look into the iGet object instruction. The iGet instruction. And here we can see we've got iGet, vx, vy, field ID. And there's the description to this. Reads an instance field into vx. Instance field is our this.power. And by reading an instance field into vx, we are reading this power into our v0. And it doesn't have to be v0, of course. Therefore, is this x parameter over there. It can be also v1, v2, v3, and so on. And we can also see the instance is referenced by v0. So this description is amazing because it directly or immediately tells you what this instruction does. And the author didn't stop by doing this description. The author also puts in an example on the right. Without this website, I wouldn't have learned Smali. And therefore, I'm really grateful to this author. Okay, let's do this once again. So what does iGet does? We take the right part and read it into the left part. So the left part is holding this value afterwards. That's all. Nice. Let's get back into our example, this one over here. Let's take this list and see how far we can get in understanding this function over here, add power, because we haven't looked up those instructions yet. And what we do is we take a look at the Smali code, we figure out our parameters, return values, and then we will try to complete the puzzle by looking up the missing instructions. Okay, let's see how good this goes. So I'm going to build this application once again in case I did modify it in any way so that we are using this code. Alright, already done. I delete this directory over here and we do this once again, apk tool D. Okay. This has been also finished. Then we go into app debug, Smali, com, app hacking, Smali1, and I open a new terminal over here. We can close this one and I'm opening the player.smali file. Alrighty, let's zoom out a little bit. Enable Java. And also just focus on this one over here. Alrighty, here I've got my graphic tablet and now we analyze the Smali code. We will slowly do this step by step and we will reconstruct the whole Java code. Afterwards, I show you a different approach, the way I like to reverse engineer this code. But for now, let's keep it to restoring the Java source code. Alright, let's do a little bit of a recap. What do we already know? So let's go. Okay, so we've got our method. This method public add power. This is our method name. So we write this down next to this. add power. This method has now two parameters. Those two. Both are from the type capital I, which means we've got two integer values. And we can also find those labels over here if you take a look into those two. These are our parameters. And yeah, the first one is int a and the second one is int b. Okay, next we've got this one over here, the return type, and it's also returning an integer value. Therefore, we can write this down over here. And now we've got our function prototype. Pretty nice, right? Next, we've got this local one. Locals one, sorry, this way. And this means we've got a local register. We doesn't know if this register is just a placeholder for a return value of another function or, for example, for an instance field, or if this local register is used for storing a variable. If we go down a little bit, we can find this one over here. And this means our local register v0 is a local variable with the name sum. And this sum is also from type integer. Okay, so let's write this down. We've got an int sum over here. We do not know if the sum now gets initialized with a value or if it's holding in value. We just know these information at this moment. Okay, then we've got our two labels, parameters. And what I like to do is I like to keep track of this. So we know int a is p1 and we know int b is p2. And we also do this for the label sum. So this label over here, this local variable sum, is referenced by the register v0 right at this moment. This might change later on if this register gets reused because this label is or this variable is not going to be used further, then this might change. But for now we know v0 is referencing the label or this variable sum. Okay, let's move on. Okay, so we did understand this part, also this part, this and this part. Now we've got this one over here. Let's focus only on this one right here. This is a new instruction, a new opcode. So let's look this up, or let's first have a look into this. We've got a const /for, then we've got v0, 0x0. Okay, now let's look this up. Okay, here we are at our Dalvik Opcode site. So we are looking for const /for. And here we've got the description. Const /for vx, lit4. This lit4 looks super strange. But if we read the description, we know what lit4 means. Puts the 4-bit constant into vx. So we've got a value over here, for example, the value 2 or the value 4, and this value gets moved into this register vx. We've also got an example on the right side. So let's have a look into this one. We have this const /for v1, then we've got this hashtag, and then this integer value 2. So we can represent numbers in Smiley with a hashtag, then we can write the decimal value, or we can write 0x, the hex representation of this value. Okay, and what's this? This is the bytecode. So this is the hex code, and if we represent this hex code in binary values, these are the ones and zeros that execute this instruction. Const for v1, hashtag int2. So this is moving the value 2 into the register v1. Alright, not that hard for this instruction. Okay, let's get back. So let's do this once again. This instruction, we've got const /for v0, 0x0. So we are now looking only at this instruction and we do a further explanation on this. We are moving 0 into v0. And if we get back to the reference, the Dalvik reference, our v0 is referenced with vx, and this one is referenced with lit4. So therefore we also know how to read this. Okay, regarding to lit4, let's take a look onto this. So we are moving 4 bits into the register v0. 4 bits, we can represent them in this way. 1, 2, 3, 4. Those 4 zeros gets moved into v0. Why do we move 4 zeros and not 8, for example, in whole byte? This depends on the compiler. So the compiler tries to save as much as space or memory as possible. And in this case, we can see the register is being initialized with 0, and 4 bits representing this value is enough. So the compiler optimized this code and used only 4 bits to initialize this value 0. Okay, let's have a look into this instruction once again and more in detail. I mean, you might think, wait, there is more? Well, let's figure this out. Alright, if we take a look back into the description, these two are referenced with VX, and this one is referenced with lit4. But what about this lit4, those 4 bits? This is a little bit annoying or confusing. Let's have a look into a real example. Let's try to store the number 10 into this register V0. The number 10, this one over here, 0xa. The hash sign is a comment in Smiley and it's being automatically generated by the APK tool. So this one is only for better readability. This does not affect the code itself. The value 0xa is being translated into 10, and that it does not disturb the code itself, a comment is being appended by the APK tool. So we can completely ignore everything after a comment, but it helps us to read this code a little bit easier. Okay, to get a view onto the bits, we need the binary representation of this value 10. We can do this by splitting this up. So we've got 2 square 0, 2 square 1, 2 square 2, 2 square 3, and 2 square 4. This one is 1, 2, 4, 8, 16. So if you want to represent the number 10, we have to add 8 plus 2. And therefore, those 2 bits are set and the rest isn't. This is the binary representation of the number 10. And if you take a look into this, we can see, yes, this number fits into 4-bit. So we can also store the number 10 with this instruction over here into the register V0. Okay, and now let's try to store the value 20 with const /4 V0, and then we've got 20, which is 0x14. This is 16 square 0, which is 1 times 4, and 16 square 1 times 1 plus it's 20. Okay. Yes. Okay, let's do the binary representation of this value 20. We do the same approach. 2 square 0, 2 square 1, 2 square 2, 2 square 3, 2 square 4. We've got 1, 2, 4, 8, 16. And here we've got 16 plus 4. Therefore, we've got this bit set, this not, this is set, not. All right. Here we can see we have a problem. If we try to store 4 bits and the value 20, this does not work. If we stick to our 4 bits, we will store the value 4 in our case into V0. So afterwards, V0 would be 4. But it might be important that the value V0 or the register V0 is holding the value 20, and 4 is not equals 20, right? Basic math. Therefore, the compiler throws an error, and we get a message that we cannot use or we cannot store this value into a 4-bit register. We have to extend this register, and I guess the next one is 16. So in our case, it would be const 16. 16 has now a lot of additional bits over here. And const 16, this works out. We can store the value 20 into our V0 register with this one. So if we write code, we do not care about this because this is something that the compiler does automatically. But if we want to patch this application and we want to increase this value over here, then we have to take care about this. And then we can figure out what's the next possible instruction for this, for example, const /16, or we can simply use const. Because const as a default is set to 32-bit. So if you encounter a const /4 or const /16 instruction, then think about this value and if you need to increase this furthermore, replace also this instruction, not only the value. So by switching out those value over here, replacing this for example with 0x14, this will not work because const 4 bits cannot hold this value. Therefore, simply remove this one over here and we are good to go. So I guess this instruction is now clear, isn't it? There we go. Let's clean up this a little bit. Okay, so we talked about this instruction. What does this do? Ah, just kidding. Let's have a look. We've got our int sum. Int sum is referenced by v0. In this case, we are moving the value 0 into v0, which means we are moving the value 0 into our sum variable over here. And I like to keep track on those registers. So I would also write down v0 equals 0. Okay? So we initialize our sum with the value 0. This is what this instruction over here does. Alright, so we also understand this one. Then we already talked about this one. There we go, we have a new instruction. This one over here. Before we look up the Dalvik opcode, let's have a look into this. So let's write this down. We've got an add int v0, p1, p2. Okay, so we have 3 registers at this instruction. And this one, yeah, I'm pretty comfortable to say what this one does, but let's figure this out. Okay, back at the opcodes, let's see. We are searching for add int. And here we can see add int vx, vy, vz. Calculates vy plus vz and puts the result into vx. Alrighty. Calculates vy plus vz. So these two gets added together. And the result is stored into vx. Okay, I guess that's also not that hard. Let's have a look at the example over there. Adds v3 to v2 and puts the result into v0. Okay, it's exactly the same. Okay, so let's have a look back onto our code. So we split this up once again. And then we say, okay, p1 gets added together with p2. And the result of this gets stored into v0. Let's replace those registers with the original labels. Okay, so let's write this down in a mathematical operation. So we've got v0 is equals p1 plus p2. This is what this instruction does. Okay, now let's replace those registers with our labels. We know our v0 is sum. Therefore, sum equals p1 is our a. A plus p2 is our b. Okay, this is what this instruction does. Let's clean this up and write it down, yeah, more clean. So this one over here is sum equals a plus b. Okay, so we also got this one. And finally, there's our return v0. We also know what this one does. It's returning our v0, which is referenced or assigned with sum, the label sum. And yeah, there we go. We have restored the Java source code out of the Smiley code. Isn't this ridiculous nice? In my opinion, it definitely is. So it's super nice to write this down in this way. We can reconstruct the whole Java code, and this will help you learning Smiley more and more. In my case, I'm not a real fan of writing this down in the original Java code, because we can simply take this function and decompile or recompile this into Java, and then we can see, okay, this is the Java code corresponding to this Smiley function. In my case, I like to write this down in a little bit different way, because we are not interested in those Java functions, or at least in those Java namings. We are more interested in which register is holding which value, because we want to patch some values to improve our power level, improve our gold, items, and things like this. And this needs to be done on register level. So we cannot simply tell sum is now equals 40. So it's not working in this way. Therefore, we have to go into the Smiley code onto the left, and then we have to patch the register, which is exactly doing this step within the initialization or something else. So now I'm going to show you my approach. It's pretty the same, but I label this a little bit different. So let me clean this up and then we have a look into this. Okay, so don't get me wrong, this Java source code is amazing, and if you like to stick to this one, of course, do this. I'm now going to show you my approach, and this is just my personal reference. If you like to do this in the same way, then feel free to go also into this labeling. But if you like to stick to the Java approach, absolutely no problem. You just need to know or just need to be able to reconstruct the code out of the Smiley function. So let's see how I would normally write this down. I start with the same approach. Method public add power. So here's our method add power. Then we've got those two parameters, and I would not name them A and B. I would name them P1 and P2. I like to stick to the registers. So in my case, I would named this int P1 and int P2. Then, yes, return value also integer, we are good to go. Just a small difference regarding to the approach we have done before. Okay, then I also move on with the next line. But in this case, I do not care about this locals one, because I'm doing this for one instruction after each other, and I'm not going to into this one and look this up downwards because I do not care about this label. Let's see if we do not care about this one, how the approach looks like this. We can now go from top to the bottom, each instruction after each instruction. Okay, then we have those parameters, and yeah, we already got those two. And of course, we can also use those labels over here. So we can say this one is A and this one is B. Not a big deal, but normally I do not care about those labels. Okay, next we've got this one over here, and we can write this down exactly as it is. This value gets stored into V0. And normally I do not like those hex values. So I would write down V0 is equals 0. Okay. Next we've got this label over here. And here we can see, okay, this V0 register has now this label sum, and this is from type integer. So I would write this down as a comment over here, but I would like to keep track onto V0 and not the label sum. So I would write down int sum. This way. Then we can move on with the next one. Here we can see, okay, P1 gets added to P2, and this result is stored into V0. And we write this down exactly as it is. V0 is equals P1 plus P2. And last but not least, we are returning this register V0. Okay. And this is the way I like to do this, because by looking into this code, we do not have to substitute those register with the labels or things like this. We can directly see, okay, we've got our P1, for example, over here. We've got a P2 over here. These two gets added. This means we've got a new value here in this register, and this will afterwards be returned. And here we initialize this register. So by doing this in this way, it's more clean for me, but this is my personal preference. If you like to resubstitute those values and stick to the Java code, feel free to do so. Okay, regarding to which approach you are using, this should be always the same. So take a look into the Smiley code and go through this line by line. And instructions that are unknown to you, please look them up. This Dalvik Opcode table is super amazing, and I'm doing this most of the time. I also encounter a lot of new instructions, and I look them up in the description. Maybe I write some little programs to understand some complex instructions, but afterwards, yeah, I know what they do, and then I write it down in the following way, as you can see here in this pencil drawing, this one over here. And by doing this in this way, even a complex Smiley code gets split into single pieces, and we can understand and write this down afterwards. It's pretty amazing if you take a look onto the left and now realize, wow, you understand every single instruction already in this Smiley code. And before you started this course, you might have even not known Smiley. So this is a huge step already, and we will get further and further within this chapter. All right? Okay. In the next section, we will extend this program a little bit. We will add new variables, maybe new functions, things like this. And by doing this, we will also repeat the steps over and over again. This might be a little bit boring, but by repeating this, you will get more and more familiar with Smiley, And after some point when it makes click, you stare at some smiley code and you realize, whoa, I'm able to read this smiley code in there. Freaking amazing. Believe me, you will have this moment. All right. So I'm looking forward to see you in the next section.